Hello everybody, I'm Simone from PLOCAN. I was the project manager of the project called NeXos. So ocean in situ sensors in the framework of the NeXos project. That's the presentation I'm going to do. And I'm replacing actually Eric Delori, which was the coordinator of the project. I was the project manager and he couldn't assist today, so I apologize for not being here. So the NeXos consortium, here you can see some of the partners, well actually all the partners which were part of the consortium, among them key players in sensors and vehicles business. There was also IEEE in charge of dissemination, and among them you can see Marum, Alciamar as a glider supplier, NKE as sensor developer and instrumentations. Okay, so the objective, we have different objectives in the project. So the main objective was to reduce the cost and increase the operation time frame of missions in the oceans. So that's why we decided to reduce the energy consumption as much as possible for some of the sensors we developed. And we develop also these sensors following the Marine Strategic Framework Directive from the European Commission, which I will show you later on. So we achieved TRL increase from 3.4 to 7.8. So we basically produce sensor close to the commercialization and could be adapted to different platforms thanks to sensor interfaces using standards in the business. Yeah, again, on one of the innovations that I will show you later on is to extend the duration of missions with optical sensor by the introduction of anti-fouling system. So to develop this sensor, we decided to create different scenarios, which are basically typical missions in the ocean. So we developed different 5 scenarios for each of the sensors that we have been developing. So the 3.0 means optical sensor. So I'll show you later on which type of sensor we developed. And the A is standing for acoustic sensor. And finally, EAF for fishing sensors, so which could be implemented in gear and fishing network. So the different platforms that we use to demonstrate and validate this sensor, you can see here, we used gliders, drifter and profilers from NKE, cable observatory, standalone ferry box, and so on. So as I introduced before, we developed the requirements of the NeXos sensor using the Marine Strategy Framework Directive and the script source. So you can see for optical sensor, passive acoustic sensor, AEF sensor, we defined, we use the different descriptor from the Marine Strategic Framework, and we apply to development of our sensors. So this here summarizes the 8 different innovations. So among them, the O1, which is a compact fluorometers. This is a PA fluorescence O1, the turbidity and CDOM developed by the company Trios. Then here the O2 sensor for the phytoplankton detection. You can see the compact version for autonomous vehicle and the bigger version for ferry boxes with a quite significant more energy consumption. And the final optical sensor is the O3 with the detection of CO2 pressure, pH, and total alkalinity to complete the carbon cycle equation. So here in details, you can see the NeXos O1 fluo matrix, which has been developed from scratches. So pretty much TRL1, which is developing the concept in lab, up to the TRL7, which is demonstrated in real condition. So here you can see the different wavelength operating for the UV version and below for the vis version. So detecting different type of contaminant in the water. This is one of the transversal innovation I mentioned before. So it's the detection and protection of biofueling in optical sensor. You can see on the right side a very impressive picture. After 3 months of operation, of continued operation in lab. So you can see the difference between one optical sensor without our system and one without, and that one was with our electrochlorination system applied. So the good things of this system is that could be applied to an existing version of the matrix through optical sensors by the application of this layer on top of the lens. So both this system detected the fouling and implemented electrochlorination as anti-fouling protection system. This is the Rico-Pesca sensors, which have been evolving into the EAF sensors. So as you can see, is one quite robust sensor implementing oxygen and fluorometers that could be implemented in real fishing gears and fishing nets. So as you can see here, this is a real application that we have done for a couple of months in the Adriatic Sea and in the Mediterranean Sea. So they have been really attached physically to to network fishing networks and launched for during a normal operation. So this could really map real area of fishing where fishermen were going, and in that sense we could support the fishing policy from European directive or national governments. This is the acoustic sensor, the E1, developed from TRL2, so the concept was already formulated, and up to TRL7, so demonstrated at sea. As you can see, the size is impressively small compared to other hydrophones. And also the energy consumption is quite small, so we could achieve long demonstration missions in the ocean. So some of the characteristics you can see of this sensor is embedded noise statistics and bioacoustic. So it could automatically elaborate the data and store into the memory of our payload. And the low self-noise is an open hardware. And as I said before, compact low power, so less than 1 watt in active mode. And implementing the standards from the OGC framework, so OGC PAC and SWI enabled. We have developed 2 versions, one serial version and one Ethernet version. Because the Ethernet has been used later on for the A2, which is an array of a passive acoustic sensor, which allow also the detection of the direction of arrival of the sound. Okay, all these all these developments been passing through reliability testings, also thanks to the University of Las Palmas de Gran Canaria and IFREMER. And the standards that we apply to the test are the national French tests, so that's the standard. So we developed hydrostatic pressure with cycle down to 371 bars, so quite strong tests, and up to 445. And then we also developed tests for cold storage, moisture, and exposure to light. Actually, one of the sensors, the EF, I can show you this one. After one of the tough tests to radiation was damaged. Actually, the lens has been damaged. So IFREMER had to provide a stronger layer on top of the laser layer. Okay. Then all these sensors have been providing end-to-end interoperability thanks to the Web of Things and standard from OGC. So here you can have a block diagram on how the communication from sensor to the data center and to our control center. And again, the sensor ML, which is the driver of each of the sensor, can be modified with a editor. So this allows us to implement and configure the sensor without the needs of any third parties tool. And then this is a summary of the web visualization server that we developed for the project. So all the sensors have been providing data into this visualizer. As you can see here, this is the O3, so the optical sensor mission that we did in Germany, if I remember correctly, this is. So this is the trajectory, and here below you can see the measurements in real time. Again, another, yeah, the same mission again. Here you can see also this is the profile. So when we launch our acoustic sensor with a profiler, you can see here this is the depth, yes, and this is the detection of sound. This is the mission we did, for example, trajectories, and here you have, let's see, what is it? The fishing, the EF sensor in the Adriatic Sea. And finally, this is the global multidisciplinary time series that you can see. It's quite chaotic, I would say, but there are several measurements together in the same layer. And these are the sensors integrated in our platforms, part of the consortium. Here you can see this is the profiler I've just mentioned before. This is the acoustic sensor A1. And then here you can see the same acoustic sensor on top of the glider, the Alcemar glider. And here you can see in the same glider we integrated two different sensors, the O1 and the A1. So as you can see, they are quite small compared to other sensors existing before, and which allowed the increase of duration also of missions thanks to the low energy consumption. And these are nice picture of our missions in Norway. Yeah, again, the server where we deploy all the data in real time. Yes, and this is the legacy with the community of ocean observation. So thanks to our sensor, we could provide this new set of instruments with end-to-end interoperability, so they can be integrated in different platforms. 50% commercially available, so reaching from TRL 3 to TRL 7 in 4 years. Coordinating partners from all over Europe, I think is a good achievement for the project, and also for the SME companies that were part of the consortium. And then open source code for plug-and-play sensors, so we allow customers to put their hands directly on the code of each of the sensors, especially for the acoustic sensor, and also to the SML editor and the data visualization website. And this is the consortium. So thank you.